Okay, let's get started. About a minute or two past time. So we're going to talk about GLMs today. So two things. There's some R code up on the website under today's lecture that may help you not have to type faster than me. So feel free to grab it. You can modify it or just run the code as I run the code, but I figured it might save us a little time today. And yeah, and lectures as usual. Okay, so today we're going to review GLMs super quickly. This is not a stats class, it's an R class, so hopefully elsewhere you've covered the basics of generalized linear models. Then a quick focus, we're quickly moving to a focus on GLMs in R. And then at the end, spending some time on accessing the results. So, you know, unlike SAS, when you print a model's object, R retains that as an object. It's not just in the print. So you're going to save that output from a model and start poking around in there. You can stick it in a data frame. You can ask for predictions from the model later on. You don't have to do all that in one statement. So we'll spend some fair bit of time on accessing results today as well as on Wednesday. Okay, some notes in the homework. I'm using now a tweaked births SM file, which I also reposted. We may continue to make small tweaks to this file. You should have your own, really, at this point, that you build from your own code. So homework 1 and 2, you know, save what you do there, so you can start homework 3 with that same code at the end of your homework. Homework, or the births SM file as we had it, I think was missing 1 or 2 variables that I want to use today, so I add those variables in. And then you'll see once we start doing some modeling on our objects, now is where it's going to start to really matter what the referent category is in our factors, for instance. And not having sort of had that conversation explicitly early on, your factors, as one of our factors at least was, had like flipped order. So we'll talk about that once we start getting model results. Being like, oh, that's a negative risk difference, but it should be a positive risk difference. And what's the deal there? That's the referent order of your factors. So feel free to download the births SM again, or just kind of keep treating that as a file that we might tweak from class to class to make sure we've got enough examples in there for the next class. Yeah. No, I mean, so births SM, as we defined it, subsetted all the variables down to like 7 or something like that. And you don't, I don't do that in my own code, and you probably didn't do that in your code. We didn't ask you to do that in the homework. So it's just like to have a quick and easy 10 variable file for the homework, for the class examples. Okay, so simple linear regression. Hey, there's a line, there's some dots, we predicted the line through the dots. I should probably be more intentional about the predict language there. As epidemiologists, prediction versus causal inference are not the same thing. Not getting into it here, we have a whole curriculum on that. But in short, we've got some points, X and Y, probably some others, and we're going to do a slope through those that minimize the least squares distance, which turns out, we'll have some slides very quickly on this, is a sort of specialized case of maximum likelihood, increasing the odds of seeing the data that we saw given the model we have. Again, odds is kind of lazy language there, but So multiple linear regression is very similar. You're just talking about building a hyperplane in multiple dimensional space. Similar though, thinking about we're forcing lines, we're forcing slopes here. That's the generalized linear part of this. There's other ways, and I think later I've got a class planned on recursive partitioning trees, which we use a lot of machine learning, that do not force any degree of linearity at all. But our GLMs here, whether they're logistic or otherwise, are forcing linearity. So worth talking about a little bit here that the way that R or SAS or whatever solve a regression question is to intelligently pick a guess of your parameters, calculate a statistic for that guess, and then repeat that using some calculus usually to find sort of chase your way to the best fit, maximum likelihood estimate. R gives you the option, and we'll explore a little bit today, to if your model didn't converge for some reason, or if there's some kind of poorly fitting model that you still want to try to jam in there, you can change the family of functions, so the family of fit functions that will help you some with that, or you can give some starting values for this computer process. You know, behind the scenes, it's picking some estimates, seeing if they start to converge, and then chasing to find the local minima or maxima or global minima or maxima on that fit function. We can also tell it to start in a certain place if we've run a simpler function. I'll give a demo of that today. I basically really rarely ever do this, but just to know that this is the underlying process, I think it's useful to hear at least once. So again, the universal fit statistic we're using here is likelihood, and that's the probability of observing the data we have under the given set of assumed slope values, the beta coefficients, and those beta coefficients would be what we are offering a fit model if we have to. Typically, you don't. And then those are also used to calculate confidence intervals. So, you know, given a little bit of wiggle, you could certainly multiply the standard error by 1.96 or whatever, and do it that way. But R will do sort of a slightly different version of that in order to get a confidence interval when you ask it to do some profiling around that point. Again, not something you really have to care about 99 times out of 100, but just want to say it the one time. So general, if we're doing a linear, a purely linear on the linear scale, generalized linear model, we would typically have a continuous outcome and maybe some continuous or non-continuous categorical predictor variables. But what about if it's a binary variable or categorical or ordinal, or some count or rate? Basically, we'll be changing that thing on the right. So we're changing the description of the distribution of what we're expecting in the outcome variable. And in R, that's pretty much all you have to do to have R pick a different, at least basic, generalized linear model. If you want to do multi-level models with a package for that, it looks very similar. The syntax looks very similar. Even I was talking about recursive partitioning trees or other machine learning techniques. We're all going to use like the same formula syntax we're going to introduce here. But the same function GLM with a different binomial or multinomial or ordinal or Poisson or quasi-Poisson or whatever is what we're going to be using. So just keeping in mind that there's a different family of functions, family of distribution assumptions that will link to the outcome variable. And then on the non-independent side, if there's interference between units, adjacent units, that's like a spatial autocorrelation problem, or if it's an infectious disease context, which I don't do any modeling in, but where there's relationships between things, you can have different kinds of models to do that. You can either squeeze your distribution of the variance and covariance into GLMs, writing your own functions, or more typically, you've got a slightly different tool than a traditional GLM, single level GLM to describe this. So clustering repeated measures of the same units, you'd be using a multi-level grouping units by time, which I think will probably offer some demo of some of those more advanced modeling concepts later in the class. So what we're going to do then is some generalized linear models. It's, I think, the only thing we cover in the core course here. Your substantive area, ID, or otherwise would do more, but we're doing generalized linear models here in EPI. And For that, what you need to know is what your outcome distribution is, what your outcome variable is, your y looks like, and then a link function. And the note down at the bottom, R lets you pick these directly, so you don't have to. Usually, you don't have to tweak the shape of your outcome variable to say, oh, this is technically a categorical, but I'm going to treat it as a binary one or as a numerical 1 and 0 in order to get my model to fit. Sometimes you do, but that's very easy to do. But more typically, you're just going to change sort of the link function at the end of the function call, and it's going to interpret that differently. So now we're getting into the code piece. So the outcome distributions that we're interested in are on the left. The quasi stuff at the bottom can sometimes actually be very useful in R. If a model's having a difficult time converging, those are a little bit looser on some of the assumptions, but they're operating basically the same way. So we're going to do a lot of binomials. One of our questions, I think, and one of the GLMs we're going to run today is probably not going to converge. We're asking for risk ratios. And it may or may not work for you, probably won't. But changing to quasi-binomial is going to relax the model a little bit and let it better. And then you'll have an associated link function with that. So identity would be for risk difference. Log would be for risk, most other things that we do, right? So log or logit for risk ratios or odds ratios. I rarely use most of those things on the right. I don't ever use pogit or probit personally, but maybe you do. I don't. Okay, so these are our first full, complete statements in R today. We're going to be using the GLM function. This is there's no package for this. It's just in stats. It's in stats or base. So it's always loaded. You don't have to load anything special, library or anything. And it's using this function syntax where there's a tilde to say this thing, this y. I read to this tilde usually as by. So I'm going to do weeks gestation by mage, and you'll see that same. In fact, you've already seen that same tilde structure in ggplot, where you're asking for facets and you want to do like this many plots by this many plots. And I think it shows up some other places as well. But you can also define that formula elsewhere. So that's a formula object. More typically, I would have that, most of the time I'm having that inside the GLM just by itself. You can also, as we've seen in other functions, define your data as a parameter, which then let you reference the individual kind of stripped down variables themselves. So that's the second one. So weeks gestation by PNC5F. In the data, births SM. So you don't have to keep writing births $, births $, over and over. And then lastly, I think most importantly, you're almost always going to save that model in some sort of an object. So that last one, M equals GLM, some outcome by X1, X2, doesn't matter. You should really read X3. And then family binomial logit to get, in this case, the that's odds. That's so that we can then play with that variable later on. We're not going to get any output when we run this. So you want to then just type M later on, or summary of M, and we'll start playing with that. But yeah, so it's most of your models are going to look like that third line there, where you're defining some family and you've got some formula. Probably going to have a data statement in there if you're working with a data frame. So again, it's specific to epidemiology. Things that we're most typically going to run are risk differences. So binomial identity, binomial log. Having taken some classes in other departments, biostats, multi-level, and social work, like some of the assumptions that we make in epidemiology, which I'm like probably pretty good in stats, an epidemiology PhD, but I'm not a statistician or a biostatistician, and didn't spend my full time on that. So definitely gotten pushback. I'm like, wait, you're asking for a risk difference out of a generalized linear model when you've got some poorly fit binary outcome, and you can't do that. I'm like, well, the entire discipline of epidemiology is doing that, so I don't know, man, you can't be. So I just want to flag that, like, there's particularly when you get into any online discussions about statistics, and our people tend to have very strong feelings about this. You may see that, like, well, that's not viable in R. You can't do that in R. And just remembering, like, well, epidemiology bends some rules. We also tested how far you can bend those rules. So whether that's the exactly how far an odds ratio models a risk ratio, or how much you can bend a generalized linear model to get a risk difference out. Just keep doing what you're doing. But these are very typically the ones that I would run. Again, binomial, occasionally if I need a model to fit and it's not fitting, I switch to quasi-binomial, and you can poke around with how those are a little bit different in terms of relaxed assumptions. So then, just to kind of expand your mind a little bit more on what we can do here, remember you can sort of, on the fly, change variables into other things. So here I've created a factor with this logical statement here. So I'm getting a Boolean out of that that's going to be trues and falses. Those trues and falses are going to be interpreted as factors, or being forced into factors or numerics. And then that model's still going to run. So, like, if you need to sort of make a quick on-the-fly change in your formula, or like, well, what if I did this, or what if I did that? This isn't, the formula isn't like Holy Land, never touch it. Like, has to be exactly the structure. You can tweak variables there. You can define variables right in line like this. So data burst, and this used to say wick equals y, but you can do an inline specification of any kind, like we did with Weeks Jest there. Okay, so I think, we're going to run some code together where we do all these things, but these are going to be useful functions for your model. So just like we had a data frame and we ran stuff like str or class or dim or n rows, or to try to get the parameters, get the shape and description of that object. The model object that we just defined in the previous slide, M1 equals GLM something or other. We also can ask questions of using functions. So giving the summary, just M1 will print a short version of the summary to the output. You can plot a model object. But you can also build your own things to plot model objects. So let's say you wanted to take your original data frame and add what the model says the variable, the outcome variable should be. So you have like your predicted versus your actual. And that's great for prediction modeling, where you can then ask for things like sensitivity, specificity, or get some confusion matrix of like what the model did really well, what the model didn't do so well. But the plot of the model by itself will produce, for GLM, some basic fit plots in a row. Names, coefficients, confidence intervals, or in the case of risk ratios or odds ratios, you're more typically, because it's log linked, you're going to want to exponentiate those coefficients or confidence intervals to get yourself back to the scale that makes sense, rather than predicting the log of the odds and the log of the risk ratio, or the log of the risk. We'll exponentiate them. Okay, and I think, so last, we're going to cut to R in just a second, so feel free, if you haven't already, to download the R file from the website, or just type along with me, which would totally be fine too. Get burst loaded up as usual. So Broom is a really, really important package, I think, and increasingly so. It used to be that I only used Broom, which is another clever R pun, to tidy objects into rectangular shapes. So we'll poke around at what one of these models looks like. But a model in R, once you sort of dig into the guts, is a list of kind of complicated objects. It's a list of a vector of the coefficients, and it's one of the list elements is the previous data you asked to fit the model. So it's sort of a complicated nested structure, like we talked about list can do. List can hold anything. This is kind of a messy object. But very typically, we want the outputs from our work to be rectangular, so that I can save it to a rectangular file or make a table with my outputs or whatever. So Broom is a package that does that for lots of different kinds of objects that need to be a little more complicated. So for instance, spatial objects, before we had this new designation of simple features where everything is a row, used to be likewise very complicated. There'd be a list, there'd be like a slot, technically a slot, but we'll get into that later. Basically a list of the projection and a list of the points and a list of the data associated with it, and they would all be different dimensions and shapes. And Broom would mush that into a rectangular object. And similarly here, Broom is going to have a tidy function. You know, I'm only doing this Broom : just to make it explicit. But once you do library Broom, just say tidy my model, and we'll give you a rectangular summary back, which we'll do with the code in a second. Or augment using my model, my original birth data set, and that's going to stick a bunch of columns on the end with what the model said the prediction was and with how the fit was and some other useful stuff. Or glance the model to give you a different kind of a summary, a one-line summary of the fit statistics like AIC, BIC, log likelihood, one line. So then in the end, and we'll run this when we run the code, using dplyr syntax, what I'm saying then is, well, take this model, tidy it, and oh, also, why don't you stick the columns on the end of the comments interval? And sort of this kind of high-level processing of the model is where we're hoping to get to when I first go to learn to run some models, but then pretty quickly moving into, I don't want to dig through the guts of the model every time. Let's use some useful helper functions for that. Okay, so we're now going to jump over to the code. So we're going to start first with a walkthrough through some generic examples. So we're not looking at births first. We're just going to review some syntax using this code here. And I'll talk through as I'm running this sort of what we're doing. But we're going to build a bunch of free-floating variables in space and run some generalized linear models on them. Let's say we've got so we'll say n is 10,000 and x1 I want to be 10,000 normally distributed variables. We can maybe do the head of x1. Okay. So we got a bunch of points that are distributed around 0 as the default for R. And maybe this one, x2 will be a binomial variable, x3 is Poisson distributed, x4 is uniformly distributed, and x5 is some sample of A, B, and C. So we're basically creating a data frame. In fact, maybe we'll do that real quick. Head, Tibble, x1, x2, x3, x4, x5, just to take a quick look at what we've done. Oh. The tidyverse loaded, now we can do that. Here's what that code did in a Tibble version. I asked for that just for temporarily, just to view it. I asked for the head of the Tibble, those things. This is data frame. So x1 is a variable distributed like this. X2 got ones and zeros. X3 has got more points. X4 again is evenly distributed with this normal. X5 is A, B, and C. We just got some variables that to work with. It doesn't really matter sort of what they are. So from that we can define. From that we can define a new variable y. And you know this, I wouldn't stress about typing this out. Type out the birth stuff once we get there. This is sort of a demo. But what we're doing here is generating an actual relationship in our heads. This will be like a simulation. So I'm generating an exact relationship to y that I know. This is the correct formula for y. And I've added some errors at the end. But this is the sort of perfect model for this data because I decided it. I've made it in space. Actually, Nat did 2 years ago, but still a good question. We can then look at some of the relationships between these things. Again, we've got this A by B syntax. So it looks like y has some sort of linear relationship to x. And we can do a box plot versus x2, which is a 1 and 0. Looks like there's some relationship there. Same thing with x3, which is our multinomial categorical variable. each of them has some different relationship, and it looks like 4 cuts off, and there has some different relationship after that. And we'll do by 5. Similar ABC. So some quick plots again, just to kind of get used to the data that we've got. Not that important. We're going to get to the regressions. Okay. So here's our first regression. It's a linear model where we're going to predict y, or model y, I should say, by 1, 2, 3. And I'll switch that for 4, 4, 5. 1, 2, 3, 4, 5. So you see, nothing happened when I ran that, other than it saved, but the output didn't. Nothing happened down in my output. If I had run that without this, so if I'm just going to run the GLM part of that statement, now I've got some outputs. It's like, okay, well, the call was this. I got some coefficients for you, and here's some degrees of freedom information, and some deviance and AIC information. There's a lot more that's behind the scenes that I can't get to because I just sent it directly to the output. So that's why we typically would want to save this. So now that I've got saved as model linear, I can then ask for the summary of that. Let's talk about what we've got here. Switch back for a second. So again, actually, you can probably see it like this. So we ran this model here. Y by 1, 2, 3, 4, 5. 1 plus C plus 3 plus 4 plus 5. And so we get a bunch of coefficients. These are my coefficients. Because some of these, so our x5, if you remember back, was an A, B, or C. And so that's going to be treated as a factor. And that factor is going to have a reference. And a default for A to be the reference, and B and C are the parameters that describe the difference from that reference level. Okay. And this is the way that will show up. Got some p-values, so we didn't do a horrible job of modeling. Not to worship p-values, but x 1 plus 2 plus 3 plus 4 plus 5 levels of 5 seems like it's a decent starting place for a model. For interaction, which I kind of glossed over actually on the slides, I'm thinking about it. Let me jump back to it. Where was that? Oh no. This is an old version of my slides. So we'll just talk about it in the code. It's old, it's like got a couple of tweaks. But if I want to add some interaction terms, we're going to use the star or equivalently the colon. And the difference here is A star B is the same thing as A plus B plus A and B turned into an interacting factor. So more typically, I'm using this one because I don't want to have to separately describe A plus B. But technically, this would let you define an interaction term without the front, which you really statistically has a lot of problems. But you could do that. So again, more typically using this multiplying factor in the formula. So running that, we get what we had before, plus x4 by x5 B level, x4 and x5 C level. So when we switch over to bursts and we do interaction by rate centricity, for instance, it's going to make more sort of intuitive sense. But just to expect when we see this colon value, that's the levels of A times B plus the coefficient, times the coefficient levels of B, the next level of A times B. So this will expand out. If you do like factor 1 times factor 2, then it's going to expand out all the permutations of those things to the reference level.
So we don't have to put x4 by itself because it's on
there. Because we did this instead of that. So otherwise, if we had done this version, we would have needed x4. If I'm following the question, x4 plus x5 plus x4 times by x5, or the multiplying version will expand it in sort of a FOIL type scenario where it becomes like first and Is that the question? but not listing it.
So like how in 134.
Oh yeah, let me move this. Yeah. No, it should just override it because it's going to be in there twice. Yeah, I mean it's the same. I think it's going to reduce the variables to the like. It's an interesting question, but I haven't done this before. Okay, like that. Oh, it's like that's great, but it's in there one time. So it's not actually doing that. You know, that formula is interpreted by other things later. It's not actually run sort of as is there. There's actually a different, which we'll get into down in the births code. If I wanted to inline in a formula square something like maternal age, getting back to our real questions, right? So if I put maternal age in there by itself, maternal age times maternal age or maternal age plus maternal age isn't going to work. So if I want to force that to be interpreted correctly, I'm going to need to wrap it in an I, which is to evaluate this, or just define a mage squared variable elsewhere in my code, which I can then put in as mage plus mage squared. But yeah, we'll get to there. Okay, so again, we have these summary. Leave that. We can ask summary, but we can also ask more things of the model. So for instance, I could ask for the coefficients of the model and get a vector of the coefficients. I could ask for the confidence interval. R is going to do a little bit of profiling to try to fit that really well, and then get you those a matrix of named rows and a lower and higher. You can of course describe with more parameters in confident if you want something different. So you know levels. Ooh. Maybe that's just 0.1, I think. Yeah. So here's a weird confidence interval that I built around the 45s. But more typically, it's going to give you the 95% if you just ask for confidence. Then we got logistic the same way. So the only thing that changed here is my family at the end. I'm saying this is use the logit link for a binomial distribution. And then we've got the summary as before, looks the same. But now, as you know, your beta coefficients aren't quite what you want, so you can exponentiate them right in line with x coef, whatever, or x confident, whatever. And we'll do the same thing with births later on, but we can also calculate those odds ourselves for comparison tabularly. And looks like we got an odds of 3.4 for one, and the odds of the other level are a little bit different. The odds ratios. Poisson is similar. Again, family, Poisson log. If you do like population level stuff, you know, if I'm building a rate for counties or something, then you would do family Poisson, and you might even have an offset in here where it'd be the denominator, the rates, how big that is. So the Poisson will work for the counts, but if you need to offset that in order to turn it into a rate, check out the Poisson help page for that. I think lastly, with this sort of toy example before we get to births, let's say I've got a bunch of models, 0 through 4. You can ask for a LRT test to compare them all. That simply. And also, I think I added this just because it showed up in some of my biostats classes and kind of interesting. But ours got a lot of neat ways to visualize models, which we don't typically do. So for instance, if I ask for that most complicated model, model 4, that's 1, 2, 3, 4, 1 plus 2 plus 2 plus 4. And I just, again, I defined inline a data frame for it with just this tibble my things and look at 10 best iterations of this. So then I could get a kind of interesting plot. Again, this is like not the epi way for a lot of good reasons, but you might be able to use this in order to reduce your model if you're thinking also about bias and variance. Right? This is a you did BIC, this is a BIC focused plot of sort of what are the most important variables, sort of from the top to bottom. So focusing on BIC of my model up here, where everything is in there, and then the BIC dropping after they drop out the least useful for prediction variable. So I just plug that to say we're not going to do a class on prediction or in non-epi ways to use modeling, but there's a lot of other tools there that can be kind of interesting and useful if you want to understand your model. Okay, let's get into the births. Get some examples that make sense. So as a reminder, now the one that I've got now at SAM looks like this, but it's just a small version of the same thing you got after homework 2, 62,000 change births. And I've got these variables in hand to work with. I wanted to add, I'm going to add a co-res so that later on when we do mapping stuff, it's easier. It's counting residents. And I kept total just to have a variable which we could interpret numerically or otherwise later on. Want to make sure Mage was in there. So it's the same data we're used to seeing. Yours should work fine, even if it doesn't have, even if it has like 100 variables, that will make a difference. So let's run the first model, and that's just me going GLM weak suggest against Mage. And so typically, if I'm just beginning to do some modeling, ideally you would define your model in advance for sort of null hypothesis reasons. But if I'm just wanting to do a quick look at what's the relationship between like A and B, that's all you can do. I mean, you don't have to save this model object. Just take a quick look. Looks like there's not much of a relationship between Mage as we defined it here, and we should know from the functional form sort of why that is. The Mage looks like this, and we didn't model, Mage we're modeling right now is a linear relationship, and that's not going to be a great fit. But you could run a, in this case, continuous, a linear, generalized linear model, just like that. Do the same thing, so now I'm using PNC5 instead of Mage. In this case, it's for a jump of early prenatal care versus non-early prenatal care, what's the impact on weeks of gestation? Looks like it adds 0.13 of a week of gestation. Right. Okay. I mean, we're like, these are really crude models for demoing, but just to start interpreting what the model outputs are, what the beta coefficients are that we're getting. Okay, so now we'll save our first model in model 1 object, and pop that big again. So now we're going to use an odds ratio we're looking for. We're going to look at, again, define this in line, weeks of gestation greater than or equal to 37. We have a variable for this that we defined somewhat painstakingly, but just to show you can, this is basically our preterm variable, by maternal age, date of birth, family binomial load. More typically you'll define your variable like we did, so we can stick preterm in there, but just to show it. So we got that GLM run, M1's now can ask for the coefficients and the exponentiation of those coefficients, and then likewise the confidence interval and exponentiation of that confidence interval to get the odds ratios for Mage. And again, unsurprisingly, but just to kind of interpret our pretty kind of dumb model here, we've got Mage with a confidence with an odds ratio of 1, as modeled, it doesn't do anything. And then here's our odds ratio confidence interval. It's a really tiny, hey, if you worship this with significance, looks great. We made it. Mage matters. Mage doesn't really matter. Okay. So let's then look at the summary of that. That's what we're looking at before. The plot is going to run this series of plots. I'll have to come down into the output, and R wants to print me 4 plots at once. So I'm going to say, yeah, go ahead and make me the first plot. These are not going to be very informative plots because the model is kind of odd, but it'll give me a residual versus fitted. This is nice, especially for continuous outcomes. And the next, the normal QQ, sort of a residual. How good are your residuals? How much are we bending the rules on GLMs? So that'll be the plot object. Okay, let's get back to now kind of the actual question again. As a reminder, the question from both 716 in this class is the impact of prenatal care, early prenatal care, and preterm birth. So let's get back to that question in more of a real way. The first thing I'll do is run a table. And getting used to what I want to sort of like prepare us collectively for what the model outputs are going to be. So let's take a look at the crews here. Got just run a table preterm and PNC5. I should say PNC, not PCT, but look at the idea. PNC. Probably more useful would be for me to run this prop table on that table, and then get these different percentages. So I can see that the difference in percent preterm for no early prenatal care looks like happens 1% of the time preterm, and early prenatal care. Wait, turn around. Yeah, that's right. So I've got more than 8%, 1%. That's weird. Oh, I need to do my margins, but yeah, I need to do the margins. That table. I don't use it so much anymore because I deployer instead. But so term, I think I want margin 2. Yeah, now the sum by early prenatal care or not early prenatal care. So sorry about that. Okay, so that's more interpretable. I just said I want the margins. I want the things that add to 1 to be on the columns. So it's the margins 2. So row will be 1, column 2. And these now from that previous table we add to 1. So I can see now that I've got more term births, 90% preterm, 90% term births with early prenatal care, 87% term births with no early prenatal care. So I have some sense of the direction of at least the crude effects that I think I'm going to see. From dplyr, you could do it, and at this point, this is how I would more typically do it. So as a reminder about how our dplyr works. As at births, grouped by PNC5 and preterm, summarize, give me the count of those within the group, and then mutate that, give me the percent is the n divided by the sum of all those n's. And I've got some more same percentages as before, but now kind of a data frame structure that I can interpret a little bit table. Note that I've got these missing ones. The GLM will automatically drop any of the levels that are missing. So if any of the variables, including the outcome variable, are missing, it's going to subset to complete cases implicitly. Now, you can do that with complete cases function or other things, but just to know that we're not going to have to fool with this once we run a GLM. But if I want to do some summary math, like right now, I'm technically making this percent out of the whole n, including those missing values, just to kind of keep in mind the difference. Okay, so let's give us some expected values. So the expected risk difference then for that previous table is going to be about negative 0.03, a 3% protective intervention on the risk difference scale, linear scale. And then if I do the same thing with risk ratio, that's looking like a 0.73, and the odds ratio should be about 0.71. Just kind of like know what we're looking for when we're on the models. This is all tabular. Okay, so I'll run a crude model then with binomial identity, a GOM. And here's that 3% protective improvement that we got, right? So I ran it without saving it, and just kind of eyeballing what the coefficient is. That's for a risk difference. Where did I go? There I am. And I'm running the logit next. So let's give me the odds ratio, and the odds ratio that it's giving me is not right. On purpose, not right. Shift to, okay. So what's happening here? So the odds ratio of 1.4 is in the wrong direction. And you can tell the referent level of your predictor variables by their coefficients. So this is saying that the coefficient attached to early prenatal care, basically saying versus no early prenatal care, right? So this is our intervention effect, which we want is 0.3. That's good. But something is wrong with preterm. Something's wrong with preterm because I'm getting an effect that's reversed. So let's take a look at preterm here. It says the factor with 2 levels. Great. And those 2 levels are preterm and term. So right now we're predicting term. And yeah, relative to preterm. We're predicting term relative to preterm instead of preterm, which is our outcome of interest, versus term. So as a plug for the 4cats package, you could also just redefine your factor the same way we defined it before. I can run from the 4cats package for factors the factor reverse. So if I do that, it's going to change the levels, switch them all, switch the reference backwards. So instead of like ABC, it becomes CBA. That's what I wanted to do was to reverse my factors. So now that I'm back on having the correct referent, there's a bunch of ways to do that correct referent piece. I just wanted to plug 4cats while I was here. I can then rerun that, rerun those two. Actually, even the previous linear model was actually in the wrong direction. It was positive 0.03 or something instead of negative 0.03. So, but now I'm on the right. I'm looking the right. So I've got a beta coefficient in my odds ratio model of negative 0.34, and the exponentiation of that, again, I can just ask for x coef model, but I'm just hand-typing it in so you can see it. I've got an odds ratio of 0.71, so that's what I'm looking for. Okay, so let's run some models that don't work. We're going to run these in succession, and a number of them will error. This is one of those things where, like, sometimes R is really helpful, and sometimes R is really opinionated. And this is one of those things where R is opinionated. And so it's like, you're trying to do something that you're breaking statistics. You need to stop. So this first one will probably not converge, so it's not going to find the answer. Let's see. I'm a bitch. Pardon me, my French. So this is I'm showing these because they don't always converge. Yeah, here's one that breaks. And sometimes I have conversion problems. And there's a lot of reasons why I'm saying sometimes. It's about like what random seed that it picked the first time, how robust the model is, how much of a bent, like how much data you have in the model. So we're running this before, and I didn't notice that I had like missing variables in my factor. Like I still had 2 young in there with 0 people in my factor. So I had a level that didn't have anybody represented in it. And R was like, I don't know what you want me to do. There's not, in some cases it would try to just drop that level. And yeah, and sometimes running previous models in the same data will also give you, I think, better starting values. And so I did at 1.6 some new starting values in here, but this is what I'm looking for, is that it's complaining. So I want to talk about what you can do if a model is, if R is complaining about your model. You can do a few things. You can switch to a different, I'm not getting all this, so we'll later. You can switch to a different family. So in this case, going to Poisson, still with a linked log, is saying these are going to treat this as a count variable and try to model it using a log link, and that might give you some better fit. Quasi-binomial is more relaxed, this is a fuzzy language, but more relaxed than a binomial, and so might fit when a binomial won't. When I ran it this morning, this one didn't fit, and this one often did fit. Or this happened in my Sunday team project also, that I had some model convergence issues. SAS may quietly give you answers that are like non-convergent, and R will more typically say this model isn't convergent. I'm going to tell you that it's like this ratio, an odds ratio of 100, like it's not right. And then lastly, this is where I'm just showing how you do it. You can get a starting value. So if you run a simpler model, for instance, or you can find a model that does converge and get some coefficients out of that and take some guesses, maybe it will help a more complicated model converge. And I rarely have to do any of this, but I just want to plug this the one time so that if you do get stuck, you've heard it at least once. So then we've got, let's get back to our risk ratio model, which we're going to run. We can also, again, define stuff in line as a binary or as a numeric, and force it to treat it as a numeric that way, which you then get a different model output. So it's trying to treat it as a factor up here, which is the right way to treat it. You could also treat it as a bunch of zeros and ones and run it through as a 0 and 1. That's what this will do. It will be to convert to trues and falses, which are then zeros and ones. And you've got a continuous variable of 0 and 1s that you're then going to predict with your model. This is the way that we're sort of bending stats on that side. Okay. Yeah.
This is the back one.
We do, or I would say did, because this first one I subset it to just like whatever 8 things. But yeah, you should be able to just stick in preterm by PNC5 in your own data. Yeah, great point. Okay, so I'm going to run a model that does converge, that gives me a risk ratio using the log link of the binomial distribution on the binomial distribution. And so then I can ask for things that I expect. So here's my exponentiation of the coefficients and the exponentiation of the confidence intervals. Your risk ratio of 0.74 between 0.69 and 0.79. So some actual epi results. Again, let's look at that. Oh yeah, sorry, go ahead. I just saved it. There's no difference.
Okay. So then why is this one work compared to one above that? That
So,
one doesn't work maybe R range.
the family binomial one, this one?
Yeah, I know.
Oh, sorry, yeah. Yeah, and actually I could have run the one that treated as a factor still, this quasi-binomial, and we can move on. But the difference here is that this is a factor. And when I ran this is no longer a factor. So this true and false is a 1 and 0, and I'm asking R to model it using the binomial link against a continuous 0 and 1, which is just one way to sort of force R to do something that it hasn't. But the output will actually be the same as if I saved quasi-Poisson one that also converges and leaves it as a factor. Yeah, good question, good catch. Okay, so again, summary we've seen before. This used to be the right way to go get your data. I'm sorry, I just ran structure of the summary of the model. So even the summary I can save as an object. Now I've got a variable S that's holding the summary of my model, and I can go poking around in there. S AIC S. I want to pull the contrasts. Here are my coefficients. But this is kind of like not the right, I mean, it works. So you can go into your model object or go into the summary of the model object and start sort of picking things out by hand if you want to, if you need to. That's why I said you can run the structure of your summary of the model, but the structure is pretty complicated. I'm still scrolling up. Okay, here we go. Get off there. So this model object is a list of 18 things. The original call, the terms, the family and how it interpreted it, a lot of stuff. And more typically, you would not want to go digging into all of these guts, right? You need a couple things most commonly. But if you do want to programmatically pull up the AIC just by itself directly without using Broom, you could do that, just $AIC or something after your model summary object. We'll have another tool in a few lines of code instead of that. So increasingly useful for me is to be able to run a model on new code or on new data. So right, I trained this model using like machine learning language, but I ran this model on a certain set of data that we saw this year, 2012 births, right? But maybe I want to use this to predict preterm birth or not preterm birth in a different cohort of people. Or if I want to get just for the same data that I ran, what the model prediction is for that set of births. So you can run just this by itself, predict model RR. It will give you the output, the sort of the Y, it gives you the Y variable for every one of those births, input variables. Now we only had one input variable in this time. This time it was prenatal care, but you'll need to. The model object has already saved the original data set that was asked for, that it used in that object. So predict your model is going to go back to original data, which it knows already has all those variables in it, and run the get the Y for each of those outputs. You could also pass a new data frame here of 100 new births, or if you want just the predictions for a certain subset, a certain sort of set of classes. You might say like, well, birth 1 is going to look like this, this, and this. Birth 2 will look like this, this, and this. You make your own data frame. It looks like what you gave it, and run predict. So the type response is, because I'm running a risk ratio, I'm technically, and because I'm, risk ratio, and because therefore it's a log linked function. If I just ask for the prediction, it's going to give me the log linked response, which is not usually what I want. I want it on the scale of the original Y variable before the link. If that makes sense. I want the risk rate. I want the risk. So that's what the type response is getting me, is a risk on the order of 0 to 1, not the log linked of that. So that's why we're if you're using an exponentiated model or a log or logit linked model, you're probably going to want to run that prediction off of type response. Okay, so these have been just a really crude X by Y, Y by X model. It's just a 2-variable model, one prediction, one call it prediction, one Y variable and one X, one predictor. So if we want to add more terms, it's very simple. So I have this first one here that's going to run preterm by PNC5 plus MAGE. I'm getting sort of what I expect, more things in my output, more coefficients, more estimates, standard errors, and then a p-value for the inclusion of that. I think that's like a p-value based on the, boy, it's a long time since I did this stuff. I'm not sure whether or not that's the log likelihood comparison of the two models, where there one variable subtracted out, or I can't remember what we're including. I mean, or based purely on the estimate. I don't think it's a model one. Anyway, I have to go digging to remember what that was. But MAGE, as again we sort of expected when modeled earlier, is not, as it's currently defined in terms of function form, not that important. Now what you might know, so the next goal here then would be to fit some squared term. Let me grab that. There we go. So I might want to do MAGE plus MAGE squared, more sort of naively, right? This is what I'm intending. But this won't work. Won't work. What's happening here? Oh God, stop. Control Shift Enter runs all your code, which is not what I wanted. Just one line, please. I hit the stop button, but now I'm attending to R's over enthusiasm. Okay, welcome back. All right, it's from just one line. So it ran, when I say won't work, MAGE plus MAGE up to the 2. I'm back to just having MAGE in there. So again, like the formula syntax isn't actually calculating that right in line. It's a formula syntax that's interpreted elsewhere. So in order to do this, I would have to use this I function, which is to inhibit the interpretation or conversion of objects. Poly is the other way to do this, which we'll do in the next line. But this just says, whatever I just defined in line, I want you to run that before you start interpreting the symbols in it. So it's, otherwise it's saying, oh, I see mage here. Mage references one of the variables in my data set. And think about how I want to interpret that in the context of a formula. You got mage in here twice. So we're saying, no, I want you to raise mage to the second. This is the same, this version, it's the same thing as defining a mage squared variable in my data set and then just sticking in mage underscore SQ or something like that. This next one is a little bit different in a way that probably doesn't matter because we're not trying to interpret this goofy mage plus mage squared coefficient. We're not trying to interpret what that means. So if I run, let me just make this big and describe the line first. So this function poly is going to, just like we had the star that expanded out, so if I had like A times B, it says really that's A plus B plus A by B. Poly is going to do the same thing by saying, oh, poly mage to the 2, so mage plus mage squared plus mage cubed, or however many of those you want. It's going to expand it out in your formula. If I don't put that raw equals true in, it's going to create, as best it can, orthogonal definitions. So if you remember back to, you ever took like a vector math class, orthogonal is like roughly normal, or like it's sort of like PCA, if you've done principal component analysis, where it's trying to define like the best way to have a mage and mage squared model, sort of so they're not so collinear, trying to spread them out apart as much as it can. Typically, you wouldn't want to do that. So in terms of interpretation, I want the mage just as it's in my data set, and I want you to square it as it's in my data set, and so that's where the raw comes in. Poly mage 2 may have a better fit because the variable's without the raw, because in that case, you're still capturing the difference of mage and mage squared, but trying to define them as orthogonally as possible, so it's at least collinear as possible. So that might make a difference if you're, again, if you've just got variables in here that you're trying to capture some of the confounding variation, then there are other ways to model this besides exactly the way the variables are. So in the same way that you might use a spline, I can't really interpret what those spline points are. I'm just trying to say fit this as best you can in the model. It's not my exposure variable. Poly may be useful there too. So we're in the poly one. Yeah. And the poly. So now I've got, now they both are a better fit rather than the linear term failed. Yeah.
Where you have to there mage, you put like a pretty big term order.
Yeah, you can put it. Yeah, you can put any number here. It will expand that to the polynomial of that variable. Okay. So it just saves you from creating a bunch of variables on the fly, especially if we've got it's actually getting totally uninterpretable to have a four cubic, starts to be strange. You do better just splining it instead of trying to, fit it with 4 levels. So it went from being from mage by itself, because we're getting this functional form problem that's our core question. It went from mage being this is not a useful predictor variable to mage and mage squared being a very useful one. We're modeling it as a polynomial. That's about all I use and all you will probably use on most of the GLMs that you'll do. So as a review, talked about how to build up a model. We're gonna do effect measure modification later. I'll demo it really quick with a class dedicated to it later on. How to interpret, how do you get your answers back out of a A times B interaction. But you got adding things, you got poly, you can stick the I in there to calculate stuff. We run different kinds of models, right? So risk difference, risk ratio, odds ratio, very traditional models. Poisson and rate variables, getting an incident rate ratio, that stuff is not that hard either. Just follows very similar. In our class, we're focusing on, I think, risk difference rather than running every possible version of the model that you do in 716. So those are sort of the guts of the modeling process for a GLM. Again, if you run, if I were to our part, I'll have I think we're talking about doing a class on this later, but I have a different kind of model object. It's going to look exactly the same. So let's do just the crude one. Oh, it doesn't need family. Not generalized linear. But this idea of the formula object, in this case, it built a tree describing my output by my inputs, and it looks, the call looks the same. If this were a multi-level GLM, so from Glimmer or L11 or whatever, it would look exactly the same. And you might have like a plus, a little nesting, describing a nesting happens in the form of syntax too. So just kind of getting used to this syntax here, expanding it out, you're going to see that through a lot of different model packages in R. Okay. So I want to finish class by describing the Broom package in practice. So we've got that risk difference. What are you talking about? We got that risk difference model loaded up. All right. So again, model R2 or model risk difference 2. We defined through all of these, right? So this is going to have the mage term in it. Could be any model though. So if you remember, if I had to do a summary of that, RD2, I get kind of a, good for a printout, but a bit of a mess if I want to do any work with that data. So if I want to be able to save the model outputs in a table, or just pull out the one coefficient I want, or I don't care about, I care about the fit of everything, but I really care about the effect on the main term. I'm not trying to do, the sort of the table 2 fallacy, if you've seen that from Daniel's classes. On interpreting every coefficient in that model in some way as if that's what that's really describing. Those are all helping me describe the main effect on my variable. So Broom has a tidy function that I just gave it the model. So I said, tidy my model. And I got my terms, I got my estimates, standard error, statistic p-value in a table. Sorry, I should be more clear, in a data frame. Technically a table, but it's the same difference. Just sort of better formatted, slightly smarter data frame. So this object then, this tidy model, I can save that as a model results, and then subset that however I want. Let's do that a little bit. So that's what it is. But then the results data frame is that. And now I can get to stuff in it. Right? So results, give me the estimate. Those are the estimates. How about just the estimate where, was it row names? And a little we've so far been lazy about the naming of our variables because we haven't had to interpret it this way, but you could then see subset. Oh, term, it's called term. You just do it like that. So what's going on here? There it is. Okay. So here are my terms, intercept. This is the one I want. Estimate where. Long road to get to negative 0.03. So that was me though taking the results data frame, asking for the estimate, just where results term is equal to PNC 5 early prenatal care. So if I want to run like 10 models and then just grab out the one piece that I want, this is going to be a useful tool for that. If you're really running 10 models, I wouldn't have written, you'd use a different sort of syntax to get to this. Like you'd use map and say, for each of these, look into the estimate and then pull out this term. So this is a little bit long looking, but you get that it's tidy, it's rectangular and tidy. Likewise, you could ask for the augment of your model. And it's actually a very long tibble. So it's got all of my original variables, ENC5, preterm, feature, etc. Yeah, so 62,000-ish, 1,000 rows. But then many other variables, including variables fitted, SE fit. Let's look at everything. There's one hack to look at it all. Do head as data frame. Whoa, data. Oh. So I pushed it back to a data frame, which is kind of dumb for printing. This is going to print everything, and Tibbles typically is smarter than that. And then I actually had. So you can see my original data ends up finishes here, and then Augment has stuck row-specific outputs. It's the residual for every question. I don't work with hats, which they move very much, but whether the Cook's value, whether that's a really important one to bend the model, etc. Standard deviation of residuals for questions about variance and model fit. So that's the augment function, and then lastly, glance. Again, if you're running a lot of models, these are really useful tools. Glance is guaranteed to give you 1 or 0 rows. If you glance nothing, then it will return nothing. But if you glance a model object, it's going to return 1 row of data with summary statistics for your model. So again, if you're running a bunch of different models and you want to, hold all those models in a list and then say, map my list of models glance, it will glance every one of those objects and give you those things back in the summary. So I think probably in the beginning when you're learning R and you're not running a whole bunch of models all at the same time, really the useful one here is tidy, just to get your model objects out, and you can then write that as a CSV if you want to. You can't write the model results out as a CSV if you just print them to the console, or if you try to print that, if you try to write that model to a CSV, it's not going to know how to do that. Because the model involves a bunch of complex parts. Okay, so this is at the end of the code. The last bit here is introducing some of the GLM stuff, but I'll just save this to when we talk about GLMs. If you download the code, you can check out what I'm doing with this somewhat complicated dplyr statement, where I'm grouping and then ungrouping, grouped by something else, and mutating in order to kind of quickly get a sense of what the risk differences I expect are, and do that all tabularly through dplyr. We'll then model this with GLMs. But yeah, I've got like a minute or two. Any questions? This is like a fast version of GLMs in R, but you've seen everything you need to do really to do the homework. We're just going to sort of spend more time with this and work on it. Yeah.
Can you go through line 185 and put that?
I didn't. Yeah, I skimmed over it. So again, this is my model object, and if you remember from dplyr syntax, if I just run this first part, this is sort of the way I'm now coding much more, just because I find it more readable and I like dplyr. So this is the same thing as this. That makes sense. So I'm just taking the model and sticking into the first parameter of the first function that I get. So then the next part says, oh, I've also got some other stuff I want you to mush onto the end of that data frame. So if I say model to confint tidy, Broom has this function confint tidy that runs confidence intervals and cleans them up a little bit so that it's got a nice name and it returns a tibble, which things like to. If I run them together with the bind calls, it's going to take tibble 1, which has 4 rows and tibble 2 and mush them together, bind those columns together. And so this is me just in one line getting getting the parameter estimates as well as the confidence intervals out. All at once. So go look at my table, tidy the first rows, tidy the model. Oh, and I also want you to bind call to stick on top of that this second thing, because this will get stuck into the first thing in bind calls. So it's data frame 1 and data frame 2. Bind calls data frame 1, data, or data frame 1 and a column. So bind calls the confidence intervals, and that's just about everything I would need for my model too.
And just know that the last flyer,
This one?
or the last type,
This one?
no, it's just you model RD2. I guess I was reading it as
Oh, I stuck it in there.
slash push bind call. But because it's within the parentheses, it just, it knows.
Yeah, this is a whole, sorry, this is a whole separate dplyr thing, basically. And I, just for clarity, I could have done confident tidy model RD2, or I could also have, I mean, passing. This is going to be hard to get back to deep in here, because it's passing it, it's cascading the pass. That makes sense. So here I can put a dot, and it would know what I'm talking about. By the time I get down to here, what bind call is getting passed is a data frame, a tidy data frame. And so confidence interval tidy doesn't know how to interpret a data frame. It needs a model, so it needs the original model. So there's a bunch of ways you could have written this. You could also write a function that's passed this once, and then it does this with model, whatever the model object is. Put it as a variable m here.
So you don't have to say the space for the first tidy and bind call. I think I was thinking you had to do a comma first,
Yeah, no, it's a good point. You don't. So this pipe here means that whatever you had over here is going to go into the first thing here. Yeah. Oh, so with subsetting, you do need a row, a blank row, comma, whatever. But with a function call, you don't. So this is the same thing as bind calls at model RD. This is probably even easier to. There, here we go. This is the purely functional syntax version without pipes. I want you to bind two things together. First thing is going to be the tidy version of the model. Second thing is going to be the confident model, which I know will always be the same length, and so this is safe to do in bind calls. I just wanted to poke, to kind of get people thinking early on how you might interact with your models in a simple way, because poking around the model guts gets tiring fast. Okay, any other questions? We're a little bit over time. Yeah.
And then you can say that.
Exactly.
Object and then.
Yeah, like this. Here's my results. And here's my. There. So now I've saved that out, those model results, or risk difference model results or whatever. You could also, just to kind of be thinking early about how you might manage models. Maybe I want to, after I bind calls, mutate and say model name is risk difference v1 or something. Now you can't see it, but I've got a model name in there. So you could do that with a bunch of models, bind them all together, and stick all your model results for all your models out in a nice table and fool with that. And we'll have a class on how to sort of get these things into tables. Really, I mean, I think I'm still working on how best to do this, but really the holy grail is never type a number in a table, right? I mean, ever. And so like that, like going from SAS back to Excel, we have some workflows that will improve on that. And there's more being developed, but that's what we're really trying to get to, is the ability to just dump your results to a square table that you can then format in Excel if you want. But don't -1.4, -1.4. Cool. All right, you should have everything you need at this point, technically, to do homework 3 and maybe even 4. 4 is the GLM one. No, I think we're going to do a little bit of EMM in homework 4, so you'll have to wait for us to do EMM, but you'll be able to do a big chunk of it already with just the GLM stuff you have now. It's not due anytime soon. I don't even think we posted homework 4, so don't worry about it. But we're getting to the end of sort of the skills piece of the class pretty quickly. All right. Thanks. Any questions, of course, come up afterwards, but 5 minutes over. Yeah.
Let's load the data, right?
Load.
Uh-huh.
Well, that's on my machine, but yeah.
Oh, I should change that.
Yeah, we'll work on your machine.
Oh, all right. Okay, but this data, is that the data after the second homework?
Yes.
Okay.
But then fewer variables.
Yeah. Of your variable. Okay. Okay.
Yeah.
All right, got it.
Yeah. Uh-huh.